implementation of a translator decoder which does the translation in an autoregressive manner without requiring the input for target language. You would recall that while training we were giving both the source language and the target language. Source language as the input to the encoder and target language as the input to the decoder. When you are building a translator, you don't give the target language as the input to the decoder. Only the source is given and it is expected to output the target language. So we are going to build that auto-regressive decoder. What does it mean? So far, we have only covered how to train an encoder-decoder or how to train a attention-based model. And in that, what we had done actually, we had given target sentence also as the input to the decoder. You will remember, this is where along with the x1 to xt, we were also giving y, which means if this is the English language, during the training, we are also feeding the target language. But now the translator need to work independently. There will be no input given here. The only input will be the input to the encoder, and based on this we will only give a startup sequence signal or a word which only has SOS. The moment it gets SOS, it already knows what was the encoder output. So based on this, the SOS and this, it should be able to give the entire translated language. So that's why we little bit improved our network from LSTM to bidirectional and all of them. Because now the only thing available to the decoder as the first word comes, the only thing which is available to the decoder is this encoder output or the context. So the richer it is in terms of retaining the information of the source language, the better will be the output. That's why these improvements were introduced. So fine, now the SOS have come, the first word is arrived, and what happens now? We have this HT, which is the initial state for the decoder, but as we know that initial state is also connected with the encoder output. This hidden state, which is the ST, is going to inquire the attention layer that for all your encoder output, what is going to be the attention weight. So this will be calculated now. Using this attention weight, it will create the context vector. This context vector is now going to help SOS understand that what should be the output, and the output will be as expected. First it will be giving the hidden state, and then the final output y1 will come. So that is where it is almost magical. You give the English translation, English word here, and you have not given anything but just said SOS, and this guy has queried the hidden state. Initial hidden state has queried the English sentence and tried to understand, given a startup sentence, I am supposed to give you this translated word, first word of y1, and there is nothing now. Earlier, the entire sequences or all the words were given at a time, and then we were iterating through them, but the words are available for us. Right now, this is not available. We have to only use y1 to predict the next value. So that's what happens. First we capture this y1 into a array so that at the very end we can use this as the complete translated sentence. So now this y1 is captured, and y1 is also used to auto-regressive. This is what is the auto-regression we discussed in the video titled as vanishing gradient. Okay. So the y1, which is the model's own output, is now used as the input for the current time step. Now this has gone to y1, and the s1, which is the previous state calculated, is now going to be used to query the attention weights. And yes, finally we have got that attention weights with us. That is going to calculate or give you the context used here along with the y1. And y1 along with c2 is going to help the model to predict the next word. This word again is collected in the array, and at some point in time we are showing y2 like that it will progress and will reach to the state of yt dash minus 1, right? T dash minus 1 will be going to the input along with the context vector for this state. Again, t dash minus 1 is t dash minus 1 will go query the attention layer. get the st-1, and then add this attention to get the final output. So this is now finally added here, and at this time that word named EOS will appear and instruct the model there is no further prediction is required. So that's what is also we are going to implement. Fair enough. So let's now get inside the code. We are not giving the input to the model, for example. So when we are doing the input, you can see that we are giving both input, which is encoder input and the decoder train input, which means that when we wanted to do the data preparation, we showed you somewhere here data and sample. In this line, we had given both the source language and the target language. Right now we are going to build a model where we want to give only the source language without the help of this. Therefore, the input and output architecture of the model has to be changed. So this is the place where we are changing the model architecture. The first thing we do, we build a encoder model. Earlier in our code, you can see that encoder and decoder was connected only through the initial state. You can see that the decoder was connecting through the encoder, decoder input was going through the initial state only. Right now we have to take this input here. Okay, encoder model is going to take the output. Okay, so we need the encoder model here, which will be called later. So there are 4 inputs which we are talking about in the decoder this time. Why it is so? Earlier, again go back and you see the decoder has only 1 input. First of all, the hidden state from the decoder we need to collect individually. So one is the LSTM hidden state, another is the cell state that we are collecting from the decoder. So this is 1 and 2. The third one is basically encoder output as the decoder input. This is the third input which you want to. And here again we are taking it as a flexible sequence length, right? Then the RNN units is 2, okay? Because the dimension is doubled up because of the bidirectional output which will come from the encoder model. And then this is the last one where the actual word, this is the decoder input where sequentially the single input will go. So that's why the shape is now no more the enter shape, but it is only, it can take only one word at a time. These are the 4 inputs to the decoder which you have created. Rest of the things are almost same. We are changing the decoder input matching with these 4 inputs. 1, 2, 3, 4. These are the 4 inputs which are going to the decoder model, and it is going to give you the output as 4 again, because these are the 3 output which any model would give. Apart from that, we also need the attention. So that's how the decoder model has been completely changed. Things to note out here is that we are using the 4 layers, trained layer from the previous trained model. One is this decoder embedding train, and that's how those layers were named properly with a suffix as train. So this is the reused layer which is already trained, so we don't have to retrain. This is the second layer which we are using, which is the attention layer. So that is also have this Q and K, if you recall our previous video. So on the attention, so you have those Q, K network, right? So that's how these layers are also now trained and the weights are learned. We have to reuse them. Next is final LSTM train layer, right? Decoder LSTM train, that's also used. The only thing changing out here, initial state and the combined input is now different. And the last layer, which is the output layer, again the dense layer, is also reused, decoder dense train. So these are the 4 layers which are used. This is again optional, where encoder all the weights I'm taking from the previous one and setting it here. It should work because without the setting weight also, because the layer names as we use the same variable, it should be the same trained model which will be used. Similarly for the decoder layers, I am now collecting those weights by the layer name. That's how the naming convention would help. So get layer of this 4 layer we spoke about before. You are getting the weights from there, a pre-trained model, and then reutilizing those weights in this decoder model. This is the new model with different set of output and input. Fair enough. This is the iterator now. So earlier within the model itself it was iterating. If you look at previous model, the model itself has an iterator built into this. Once you give the input in the training and you give the input in the decoder, which is the target language, then using the target language it will iterate. But now we don't have the target language. So that is where we are now building a translator program, which is a iterator by nature, where how the iteration will happen, just look at this one. So whenever you give the input, the entire input goes to the encoder and then the encoder output is collected. That's step number 1. Then the second step is nothing but SOS word. You can see the only thing which we have in hand to feed into the model, the encoder input, and decoder don't have anything at all. Decoder only has SOS, which is fixed word. So the first word which will be fed to the decoder is SOS. Apart from that, decoder don't have anything, no training data or nothing. So once this SOS is given, it will utilize this hidden state, initial hidden state, to encode the attention layer and thereby creating this context vector. I am just rerunning it, so you can just see that SOS is given, and once the SOS is given, this is where the weights are calculated. From the weights the context vector is formed and then they are concatenated, and then that is used to predict the first output. You come back to our code now and you see it is same thing done. Encoder input has been given, output has been collected, and this is the fixed word SOS, which is in a loop given to the model as the first input as the SOS. Here the target sequence is SOS, and collected input of the encoder output is now given to the model, right? And you are asking attention layer, querying the attention layer, you give me the attention weight for that, along with the next hidden state and the output token. So the output token now becomes your y hat, which is whatever in a format, in a vectorized format, which from where you will take the output and convert it as a word, and then check whether it is EOS or not, end of sentence or not. If it is end of sentence, then you don't proceed at all. But if it is not, then you go and decode the sentence, okay? I mean, collect it in the array, which we showed in the animation. You collect it in the array and then set this as the target sequence for the next time step, exactly matching with our animation, right? So this target sequence is now y1. y1 will be again fed into the decoder, and decoder automatically will call the attention layer to give the attention weight. Well, each of the time we are also collecting the attention weight into this array. So now this code is in action. Let's see. We are doing similar type of sample generation from our training data, and then finally this is the place where we are calling this guy, this function decode sequence, only one given. Earlier, if you remember, during the previous attention visualization, we were giving both lang1 and lang2. Right now lang1 given only, source. Internally model is now playing this loop, while loop, right? And this while loop is in turn calling the attention, and so everything is happening there, giving you the prediction word, prediction words, because all of them are now collected to the decode sentences which we are returning. Okay, and this is what we are now plotting here. So let's see how effectively it is able to plot. I mean, more than plot, whether it is able to predict at all or not. First time when I did this, it was not at all predicting. A very common pattern which I observed is that it has a tendency to predict the same word again and again. Given a SOS, it will try predict a random word, and then that word will keep on predicting. This EOS will never come at all. So it will finally has to terminate by the entire decoder, the decode sentence. The number of words which is there, it will hit there and then it will terminate. So it will predict a large amount of words which are random in nature, and mostly they will be repeating. That's the pattern which you will also see when you are trying to do a decoder implementation or a sequence to sequence model implementation will most likely result something like that. But don't get disheartened. Your model still may be working. Everything is right. All you need to do a little bit of hyperparameter tuning. For example, in my case, what finally gave a result is very trivial. I'll just show you. When I was preparing the data adjustment, you see I have introduced this portion, shuffle the data. So now the data is not sequentially coming, but before the data got generated, I did one round of shuffling. And this solved the problem, okay? Because I anticipated that it is not learning a driver's pattern from the training data, that is why when the support for the model was withdrawn in terms of training data not provided, it was not able to predict after SOS what I am supposed to do. You could possibly also increase the embedding dimension, because then from the encoder it will have more enriched information. You could do many other customization. For example, LSTM parameter, you can improve the layer of attention. Okay, all those you can increase the training data set. All those are the hyperparameter tuning. If you do all of them properly, this theory will definitely work. So at the very end, I want to show you some of the prediction, how it has happened. For example, you can see this is the language 1, which was Tom is a teenager, and the expected output is SOS Tom is in teenager, and then finally EOS. So this is where the prediction has happened, and this is the prediction result. Absolutely brilliant. It has predicted correctly. Okay. So here it goes, plotting of the same thing. Here again you are seeing that whenever there is a one-to-one translation possible, attention has worked brilliant, right? Whenever it is not so, is possibly here. It did little bit good. Teenager one shifted, it should have come here. Okay, is very poor, but is together little bit weight it has captured. Moving forward, you can see subsequently this has done little better. As you see, diagonally the colors are lighter. You will automatically know that it has done better. The attention weights are better. This is where it has done very good. This one is done good. So okay, and the last thing is that the attention plotting was not perfect, but it actually, whenever there is a one-to-one correspondence was there, it predicted, it actually mapped them with the proper weight. Okay, and we also said that with more hyperparameter tuning, this attention weights can be further improved. Going forward, we'll be now going more towards the attention work, and we'll finally move into the transformer architecture, where the recurrent nature will also be removed from the model. So we'll see more improvements, and gradually, step by step, we'll go towards the large language model, and that is the day we are waiting for. See you then in the next video.